This is the AI News Flash for June 20th, 8 a.m. UTC. First up, researcher Ishanu Chattopadhyay has published a theoretical framework that proposes to measure intelligence in the language of thermodynamics, titled The Thermodynamic Measure of Intelligence. The framework defines intelligence as the lawful amplification of rare but valid futures. In other words, a system increases the probability of outcomes that would be unlikely under passive dynamics, yet remain admissible under the constraints of its domain. The core of the paper is that an intelligent system must model the world, including its own place within it, leading to what the author calls recursive self-simulation. He derives a necessity statement that high amplification is impossible unless the internal simulation identifies rare valid futures with high fidelity, and a near sufficiency statement that when fidelity is high and the simulation contains an effective policy, the achievable lift approaches the actuation limited optimum. The measure claims to place everything on one universal scale, from passive matter and feedback controllers to large language models to humans as text generators and even Maxwell demon-like information engines. It is an ambitious attempt to answer what intelligence is from physics. Next, a research team, including Johns Hopkins University, has published a method to keep mixture of experts' models well calibrated even when the data distribution shifts. Authors include Suchi Surya and Rama Chalapa, and the work was accepted at the major machine learning conference ICML. A mixture of experts model switches between multiple expert submodels. Calibration means aligning the probabilities a model reports with how often those outcomes actually occur, which matters for trusting its predicted confidence. The team studied how routing mechanisms interact with expert-level calibration under distribution shift. They show that calibrating each expert is sufficient to calibrate the whole model in hard-routed systems, but is insufficient for soft-routed ones. To fix this, they propose an adversarial reweighting that penalizes the calibration errors of the routed aggregate under distribution shift. Across model classes, prediction tasks, and shifts, it improved the accuracy calibration trade-off, both on average and on difficult subsets of the data. It is a step toward making AI probability outputs more trustworthy. Finally, a team from SEED, the research division of Electronic Arts, has published a paper proposing a framework to augment in-game AI characters using deep reinforcement learning. Immersion in games depends not only on graphics and audio, but on the quality of in-game characters. Producing believable behavior with hand-coded systems is hard, and the resulting limitations often break the illusion of realism. Machine learning models could create more human-like characters by learning from interacting with the game or from player data. The authors present a framework for training reinforcement learning models with requirements tailored to game AI and game development. The paper presents examples of games with reinforcement learning augmented AI and describes the practicalities of deploying player-facing agents in modern games. It also identifies bottlenecks and hard problems as promising research directions to accelerate machine learning adoption in the video game industry.
That's all for this AI News Flash.